Hey kids, real quick lesson, so let's not waste any time. Do this problem. Great job choosing choice A. B. Two. Two. Because the arrows point towards A and away from B. When we're talking about electric field diagrams, we always imagine a small positive test charge. A small positive charge would be repelled by B, attracted to A. So A is negative, B is positive. Hooray! Okay, let's watch a quick video reviewing the Millikan oil drop experiment.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall.
This is not a
When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Okay, so the key idea is that the oil drops were negative because they had extra electrons, and Millikan put them between two plates. He had a positive on top and a negative on the bottom. So the oil drops hovered in the air because they were repelled by the negative and attracted by the positive. Why both? That's my question. Why did Millikan have two plates? Wouldn't it work if he did either of these two things? Wouldn't it work if he just had the oil drop and a single positive charge? Or the oil drop and a single negative charge? Could these also allow the electron to float in the air? They might, but this had a really, really important benefit. And a big clue, what's the benefit? Here's a clue. A free body diagram is always a great clue. This is a free body diagram for the oil drop floating in the air. Two forces Fe, Fg that are equal in magnitude. So why was this much better at creating forces like this than either of these two setups? Tell me right now if you have any idea. What do you think? What advantage does this have that these don't? It's not super obvious, but it's a really cool thing. The force from the positive charge from a single charge depends on distance. Remember, k q1 q2 over r squared. The force from a negative charge also depends on distance. Somehow, when Millikan set it up like this, he made it so that the charges experienced a electrostatic force, Fe, that didn't depend on distance. Fg is constant. Everywhere you are on Earth's surface, it's always m times g. Fe is Eq. To make the experiment work very well, he needed to make Eq constant everywhere inside the plates, not just at one specific location, because that made the experiment a lot easier. So to recap the idea, how would the electric field diagram look for just a positive and just a negative? Where's the strongest field? Where's the weakest field? Please draw that. Well, please explain how it would look right here. Where's the strong field? Where's the weak field? What direction do the fields point? What's that? Oh, thanks, Bunny. Yeah, that's right. The strongest fields will be closest to the charge. Away, away from the charge. And then they'll get weaker and weaker. Strong field, weaker, weaker. Strong field, weaker, weaker. The strongest field is also near the negative, but this time it's toward the charge. Strong field, strong field, strong field, weaker field, weaker field. The strongest field is near the charge. Notice I erased the oil drops so that um, notice I erased the oil drops so that because electric field doesn't depend on the charge being affected. The field is created by that big negative and the big positive. Whatever charge is there, whether it's an oil drop or a proton or electron or anything, it's still the same field. These are electric field diagrams for a positive and a negative charge. So basically, Millikan didn't use these two. He used this. For this reason, let's say there's 3 points, point P, point Q, and point R. He wanted the field at P, Q, and R to be the same. But aren't they not? Look at the positive plate. Isn't the field from the positive plate strongest at P and weakest at R? And look at the negative plate. Isn't the field from the negative plate strongest at R and weakest at P? It is, because of the formula, Coulomb's law. So how did he get a constant electric field? How could he make E constant? He wants Fe to be constant, like Mg. M's constant because it's the same oil drop. G's constant because it's the same earth. Q's constant because it's the same oil drop. How did he make E constant? By using 2 plates. There's a really big idea of why E is constant. The reason, the body will tell you. E is constant because it's a vector sum. Yes, it's a vector. We find the vector sum. Great job. If I have just a positive plate, I'll have the strongest field close to it. Then it'll get weaker and weaker and weaker. This is not a constant electric field. That's not what we want. If I have just a negative plate, I'll have a weak field, weak field, weak field, then stronger, stronger, stronger field. Also, not a constant field. But if you have the 2 plates together, the vector sum is constant. You have a strong field plus a weak field on top, and a weak field plus a strong field on the bottom. They're both in the same direction. They're both downward. And that helps us get a constant electric field. We have a constant downward electric field. If it affects a negative oil drop, it can create an upward force that'll exactly cancel the constant downward force of gravity. That's what Millikan did. Otherwise, you'd have to like go up and down all the time and measure like the height of the oil drop, and it would be much more difficult. This way, he didn't have to measure the height of the oil drop. It didn't matter where the oil drop was, because no matter where the oil drop was, E was the same, thus Fe was the same. And that's how he knew Q. That's how he could find Q. He used plates, not point charges. You might think it worked with point charges, but mathematically it just doesn't work out. If you have like a positive on top and a negative on the bottom, you can find the force upward. I'll call this Fe plus. and the force from the bottom, Fe minus. So let's say I put, so let's just quickly review what electric field is. If I put a negative charge right here, it'll be attracted upward by the positive and also repelled upward by the negative. And if it were a positive charge, those would both be reversed. Anyway, the total force will just be the sum. Right, bunnies? Right, Mr. Lamb? Okay, thanks. Good job. You could find this, and it is true that in this case, you still have the same effect where the closer you are to the positive, the farther you are from the negative, and it kind of balances, but it doesn't perfectly balance. So basically, I'm saying if you did k q1 q2 over r squared and k q1 q2 over r squared for these two, for any charge somewhere in the middle, maybe right in the center, you could put a charge in here. You could put some mystery charge, some mystery test charge. If you did that, you could find the force on that charge. And as you know, this is a review, the force on the charge you put here depends on this charge. So you divide by that charge so it doesn't matter. Anyway, the point is, this would almost work, but not quite. It wouldn't actually be constant. If you did the math, you would not get a constant because at a different height, it will be different strength. So this doesn't work, but if you don't use point charges, if you use plates, so they have to have two big, flat, thin plates conducting metal, one a positive charge, and one the exact same charge, opposite sign, and they're parallel, you do get the very important idea, constant electric field. So if I drew the electric field diagram, I won't have any big arrows and small arrows. They'll all be exactly the same size. The electric field is constant. This is really useful in a lot of science and engineering and electronics applications to have a constant electric field. This is called a capacitor. Two plates, one positive, one negative, that are parallel and opposite charge is called a capacitor. It's used to store charge when you don't want a battery. It's used in any sort of clock application. It's used in a lot of things. It's used in defibrillators. It's used in camera flashes. It's used in so many electronics all around the world. A capacitor. But what we learned today is it makes a constant electric field in the middle. And that's why we don't ever use these formulas with the K, Q, and Q2. We don't care. We know it's constant, and that's all we need to know. We don't really need to care what the charge is and how far apart they are. All we need to know is this magical ratio, Fe over Q. If I put like a 1 Coulomb charge there, it'll experience a force of like, I don't know, 5 newtons. If I put a 2 Coulomb charge anywhere inside those same plates, it'll experience a force of 10 newtons. And if I put a 3 Coulomb charge in between these plates, the force experienced will be 15 newtons. For every 1 Coulomb of charge, that charge experiences 5 newtons of force. 5 newtons per Coulomb is the ratio of force to charge. 5 newtons per Coulomb is the electric field strength between these plates. That was review. You should have known what electric field was, but in case you didn't, that's what it is. The only idea I have for today is it's constant between the two parallel plates of a capacitor. So what was the point of this lesson? That and this. E equals Fe over Q. So for a single charge, you can use the Coulomb's law formula, Kq, Q over R squared, and cancel a Q. But that's not really useful. We never do that. If you have multiple charges, or even like if you don't know what's causing the force, you can still find the field. What's causing the force could be multiple charges. It could be like this, the top plate and the bottom plate. Well, if you have two forces causing electric fields, they actually create two electric fields. We can distribute the Q. And wait, Fe over Q, that's the formula for electric field. So basically, what I'm trying to say is, electric fields, if one charge makes one electric field, like the top plate makes electric field E plus, and the bottom plate makes another electric field, the bottom plate makes electric field E minus. The total field will be the vector sum E plus plus E minus. I call it E total to be consistent. So that might be a little weird. Let me show you an example. I think last lesson we did a like weird problem where we had like a like a lamb throwing a football at like a goat. That's what goats look like. Perfect. Well, if we want to find the field at this point, we always call the points P because the point starts with P. We could find the electric field at point P by adding up all the electric fields. And that's why, basically, if you saw the simulation thing I did last week, the field is really complicated when you have a lot of charges because every charge you add in to the area affects the total electric field. Let me show you what I mean. Here I have one charge. It's making a field. Right here, the field points to the right, and it's pretty strong because it's very close to the charge. If I put another charge over here, this field got even stronger because now there's two charges. Basically, at every point, the field is affected by this charge and this charge. It's the vector sum. So I could have a whole like crazy setup of electric fields from electric charges. And if you were able to like beat level 3 of the hockey simulation thing, then you know this for sure. Every single point experiences electric field from every single charge. But don't worry about that. The relevant thing, E equals Fe over Q. The total field is the vector sum of all the fields from all the charges. And it's equal to the charge, it's equal to the force felt by a charge divided by that charge. Which sounds kind of weird, but it's really useful for a lot of things. And I'll stop there. Great job.